The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Lewis structures. So I tell students who have sort of no background in chemistry before they come into this class, and there always are some, that there are some topics in 511.1 that having no experience with the topic is actually a good thing, and Lewis structures is one of these things. I think if you've seen it before, you're like, oh yeah, that's easy, I know how to do that. You don't practice, and you get on an exam, and you're like, oh, wait a minute, I forgot how to do this. And the students who haven't seen it before know all the rules and just get brilliant, perfect scores on the exam, and the other students are like, man, I forgot how to do my Lewis structures. So here are Lewis structures. We're going to go over them. So I really like Lewis structures because they're relatively simple. And they work like 90% of the time. They are the correct structure. And I'm a big fan of simple things working. If you wanted to get from 90% to 100%, you'd have to use Schrödinger's equation. But you can get 90% just with the simple Lewis structures. I'm a big fan of that. I love it when simple things really work pretty well. OK, so in Lewis structures, the key to this is thinking about the electrons being shared so that you get a full valence shell. And having the electrons distributed in such a way that all of the atoms have the number of electrons that make them happy, which is usually 8 electrons, which is an octet, that noble gas configuration. So every dot in a Lewis structure represents a valence electron. And we can then look at some atoms and put dots around them to indicate the number of valence electrons. So we also have to know how many valence electrons atoms have. And so why don't you just practice with that with a clicker question. And here's the part of the periodic table up here if you need it. All right, I'm told 10 seconds. Everyone was crazy fast. Yes. So 7 is the correct answer. You could look at the periodic table. And sometimes with these, it's a counting thing. So this is one where you want to always double check if things don't make sense. All right. So we can put 7 electrons around fluorine. And we'll have 2 fluorines here. They'll both have 7 electrons around them. And now I'm going to jump to another slide, but I'm going to show you the 7 again in case you haven't written them down. If you don't want to, they're not in your handout, but that's probably OK. So when you bring them together, you can bring them together in such a way that they can all share. And so if we put in green, then one of the fluorines, a 7, and then we put in blue the other fluorine 7, you can see that they can share 2 in the middle, and both are very, very happy. So just thinking about this really simple idea, how many electrons will give you an octet, will give you 8, and how can you put things together in such a way that allows for that to happen. Now, there are a few atoms or elements that do not want 8 in their valence shell, and hydrogen is one of them. It just has that one S. So it only wants 2. That's all it can handle. So this is an exception. Hydrogen is going to want 2 electrons. Hydrogen loves to interact with things, though. It interacts with lots and lots of things. And here, hydrogen with its 1 valence electron is interacting with chlorine with its 7 valence electrons, and they are sharing 2 electrons forming a bond together. So when we're talking about Lewis structures, we're talking about different kinds of electrons. So we are talking about bonding electrons, the electrons that are involved in the bond, and also lone pair electrons. So chloride in HCl is going to have 2 bonding electrons. One was its, and one came from hydrogen. And it's also going to have 6 lone pair electrons, or we could say 3 lone pairs. So when we say a lone pair, that indicates 2 electrons there. So it has 1, 2, 3, 4, 5, 6, or 1 pair, 2 pairs, 3 pairs. Now there are rules to Lewis structures. And here's the complete rule. In your handout, this wouldn't fit on 1 page. It's on 2 pages. And these rules, if you do work these problems, you will remember these rules, and they become pretty easy. But it's important to work Lewis structure problems so that the rules become really familiar to you. And it takes time to work Lewis structure problems, so don't wait to the last minute to start this problem set. There's a lot of Lewis structure problems on it, which means it's not difficult, but it's going to take some time. All right, so let's briefly go over these rules. First, what you want to do is draw the skeleton structure. Just put the atoms down. Hydrogen and fluorine are always going to be terminal atoms. Don't put them in the middle of a molecule. That gets chemistry professors really upset to see hydrogen in the middle with lots of bonds to things, so don't do it. And typically, the element with the lowest ionization energy goes in the middle, and there are some exceptions, and we'll see some of those exceptions. But that should be your first guess. You want to count the number of valence electrons. If there's a negative charge, you need to count that in. Or if there's a positive charge, you need to subtract that from the total. Then you want to figure out the total number of electrons needed, so everyone has their full valence shell. You need to subtract these 2 to get the number of bonding electrons. And here are some of the things that it's really easy to make math mistakes here. So if your structure makes 0 sense at the end, go back and check your math. Assign 2 bonding electrons to each bond. If any remain, you want to think about whether you have double or triple bonds. And there's only certain kinds of atoms that can have double and triple bonds. So be careful where you're putting your double and triple bonds. If any valence electrons remain, those are lone pairs. And then lastly, you want to figure out the formal charge on all the atoms in your structure to make sure that this is a valid structure. And we're going to talk about formal charge. So first, let's just try an example. And your sheet has 2 examples on the same page. We have HCN, and we also have CN minus. So we're going to do HCN first. So don't fill your entire page, because you're going to have to write things for CN minus as well. But before we start, we need to figure out which atom is likely going to be in the middle. And so why don't you tell me what you think on a clicker question? OK, 10 more seconds. Yep. So here, again, we want to have one that has the lower ionization energy. And you also want to consider other things like hydrogen can't be in the middle. OK, and it was written that way, but sometimes they're written in a way that is not as straightforward. OK. So we'll put that up. All right, so we'll go through the rules, and we'll try to work this out. So first, I can write, start, so right over here. So number 1, we're just going to write HCN with C in the middle. So that's the first thing we're going to do. Next, we're going to consider the valence electrons. And you can just help me out by yelling things out. How many valence electrons does hydrogen have? What about carbon? Nitrogen? And you can always check me on my math. How much does that equal? Excellent. There's nothing like adding simple numbers in front of 350 people to really put the stress in one's day. OK, so to have a complete full valence shell, what do I need for hydrogen? What about carbon? 8 to be complete. Nitrogen? 8. And I think if we add this up, we should get 18. How's that? All right. So for 4 now, we're going to subtract these numbers from each other to tell us how many bonding electrons we have. So we have 18 minus 10, and we should have 8 bonding electrons. For 5, I'm going to now assign 2 per bond. So I'm going to put one here, another here, another here, another here. So I've assigned 2 per bond. And now I see if I have any left. Do I have some left? I've used 4. I had 8. So yes, I have 4 more. And if you have more bonding electrons, then you are supposed to assign those bonding electrons and think about whether it's allowed to have double or triple bonds. Can hydrogen be involved in a double bond? No. Carbon, nitrogen? Yes, or a triple bond. So I have 4 more, so I'm going to put 1, 2, 3, 4. So I'm going to have a triple bond between my carbon and my nitrogen. And now I'm good. So now I want to see, do I have any extra electrons? So for this, I had 10. I used 8, so I have 2 left. So I'm going to assign those 2 as a lone pair. Should I put them on hydrogen? What about carbon? No, carbon already has its 8 because it has 4 bonds. So then I'm going to put it on nitrogen. And then the only thing left is formal charge, which we haven't talked about yet. So before we do formal charge, I just want to do the same thing with Cn minus. And I will say, if you want to draw triple bonds, that's fine too. You don't have to indicate the dots as bonds. It's perfectly fine to write out a triple bond. So I could have written this as well. OK, so let's look at Cn minus. So how many valence electrons does carbon have again? 4. Nitrogen? 5. Am I done? No, I need to add 1 because there's a charge on this molecule of -1. So I have 10 again. 3, I'm going to figure out how many electrons I need to complete my valence shell. How many from carbon? 8. Nitrogen? 8. So now I have 16. I will subtract now 16 or 10 from 16 and get 6 bonding electrons. And I'm going to assign first just 2 of them. So I'll assign 1, 2 here. And then this is to assign. 6 said, do you have any left over? I had 6. And I only used 2, so the answer is yes. I have 4 more. So I can put those in. 1, 2, 3, 4. Again, we're going to have a triple bond. And then we ask, are there any electrons left? So we had 10. We used 6 of them. And so we're going to have now 4 more here. So now I can assign, this is not complete for carbon, So I can put a lone pair on carbon, and I can put a lone pair on nitrogen, and now they have their complete octet. And we get to assign formal charge. So I could write it this way, or I could have written it with a triple bond here, and don't forget to put the charge on the end. All right, so now let's consider formal charge, because we're never done with our Lewis structures until we've considered formal charge. So formal charge is a measure of the extent to which the atom is really kind of lost or gained an electron in the process of forming this covalent bond. So as we'll talk about, it's not the same as oxidation number where you have like sodium +1, but there's some differences in how many are brought to the table and what it ends up with in the end. So there's an equation which you'll have to learn, but if you do enough of these problems, it'll be stuck in your brain and you can't purge it even if you want to. And so formal charge, Fc, is equal to the number of valence electrons, symbol V here, minus the number of lone pair electrons, minus half of the number of bonding electrons. So at least this equation makes sense. If you forget what they mean, you can probably think about it, and it'll come back to you. So in doing these formal charges, you want the formal charges to add up to the charge on the molecule. So if we had HCN, that's a neutral molecule. So the sum of all of the formal charges must be 0, or you did something wrong. If it's Cn minus, the sum of the formal charges has to add up to -1, or you did something wrong. So this is a good way of checking your math. So always remember that the sum needs to add up to the total charge on the molecule. If you remember that, that's a really good check to make sure you didn't make some kind of weird math mistake and add things wrong and have an appropriate number of lone pairs or something going on. OK, so let's calculate formal charge now on our Cn minus molecule up here. So the formal charge now on carbon here. So how many valence electrons does carbon have? 4. How many lone pairs does it have? It has 1 lone pair, 2 lone pair electrons. This is the total number of lone pair electrons here. And then half the number of bonding electrons. So it has 6 bonding electrons, and half of that is 3. And so that should add up to a charge of -1. You can also, instead of thinking half the number of bonding electrons, you can also just think about number of bonds if you want to do this. All right, so let's see if you have the hang of it. Let's do a clicker question. OK, 10 more seconds. OK. Most people got that right. I can't actually read the number, but that was very good. It always seems wrong to put 0 as the answer, but that is, in fact, the answer here. So if we look at this again, we have 5 valence electrons on nitrogen. We have 2 lone pair electrons. And we have 6 bonding electrons. Half of 6 is 3. And so that's 0. Or you could have said, well, if this is -1 and the charge is -1, then that have to have been 0. Otherwise, Professor Drennan did something wrong. And that's just not possible. So the answer there would be 0. And you can see that the total charge total formal charge is -1, and the total charge of the molecule is also -1. So again, formal charge does not equal oxidation number. It's something special. It tells you kind of in this arrangement of atoms in the molecule, did this atom kind of come up with a little bit more at the end or a little bit less, depending on where it started from and where it is. And we want in these structures for the formal charge to be low. So we can use formal charge to decide between Lewis structures. So the structures with the lowest absolute values of this formal charge are more stable structures. So if you have really high formal charges, that means that molecule isn't really very stable. Because you want low charges. You want lower energy. You want things to be in a more neutral and happy state. So we want to figure out which ones are going to have low charges. So let's look at another example. Thiocyanate ion, and it has a carbon, sulfur, and nitrogen in it, and it has a charge of -1. So I might tell you the ionization energies for carbon, sulfur, and nitrogen, and then ask you which atom do you think is going to be in the center of the molecule. So what do you think? What's in the center of this molecule based on those numbers? Just yell it out. Sulfur. So sulfur has the lowest ionization energy, and I told you that's usually the thing in the center. But you can start with that. It's always good to start with that. But then you want to check the structure and make sure that a structure with sulfur in the middle has the lowest formal charge. So let's take a look at that. So we can draw structure A with sulfur in the middle, and then calculate the formal charges on that. And if we do that, we see for the nitrogen here, nitrogen has 5 valence electrons. It has 4 lone pair electrons, and it has half of 4 bonding electrons. So it would have a formal charge of -1 in this particular structure that has sulfur in the middle. We can look at carbon. Carbon has 4 valence electrons, 4 lone pair electrons, and half of 4 bonding electrons. So it has a charge of -2. Then we can look at sulfur. Sulfur has 6 valence electrons, 0 lone pairs, and half of 8 bonding electrons. So it has a formal charge of +2. So overall, this does equal the -1, so it's a valid structure. But is that the lowest energy one? We also could put carbon in the middle or nitrogen in the middle. So let's look at what this does for us. So with the formal charge on nitrogen now, we have 5 minus 4 lone pair electrons minus half of 4 bonding electrons minus 1, so that's the same. Now we can look at carbon. We have now just no lone pair electrons. It has 4 minus 0 minus 4, half of 8 bonding electrons, or 0. And for sulfur, 6 minus 4 lone pair electrons and half of 4 bonding electrons, or 0. Next, structure C, 5 minus 0 lone pairs minus half of 8 plus 1. So that one's different. Carbon, we have 4 valence electrons minus 4 lone pairs minus half of 4 bonding minus 2. And for the sulfur, 6 minus 4 lone pairs electrons, half of 4, or 0. So now with the clicker, tell me which is most stable. All right, 10 seconds. I think this can be 98%. That's what I'm thinking. I'm feeling good. Well, close. close. Yeah. What? No, no. Sorry. It should be B. Yeah, it should be B. Yeah. Sorry. I actually, yay, there we go. Yeah. B is correct. So if we just look at it over here, it has the lowest number of formal charges, so the answer is B. Okay, let's start with this simply. Who wants to tell me why 1, how they could look at this and realize 1 was not the correct answer? I think this is on. Give it a try.
1's not correct because if you look back at your atomic radius chart, this is pretty much doing the exact opposite of that.
Yeah. So helium, definitely not the biggest atom there is. Okay, so 6 got a lot of attention, and so did 2. And ionization energy, electron affinity, and electronegativity are definitely connected to each other. But there is a clue that electron affinity is would not be the correct. Does someone want to say what you might have noticed?
For electron affinity, it increases and then stops at the noble gases because noble gases do not want electrons. So in this particular chart, all the noble gases are like the highest ones in the relative area, which would mean that electron affinity would be incorrect.
Yep, that's right. So the noble gases were the clue. So, thanks. Yep. And so if electron affinity also is not high at the noble gases, they're also not electronegative. Noble gases just don't want extra they don't want to lose electrons, they don't want to gain electrons, they just want to be left alone. So that's, this trend is for ionization energy. And because noble gases want to be left alone, they don't want to lose any of their electrons. Great, so this is good to be thinking about because we're finishing up now for the handout from last time, and we're going to be talking about electronegativity again. We never move very far away from a lot of these topics. They just keep coming back, so we just keep reviewing them. All right, I don't need 2 microphones, although, I don't know, I kind of like having this one. Anyway, so let's take out the handout from last time, and let's finish it up. We were talking about formal charge. And we had looked at examples where we calculated formal charge, and then we looked at which structure would be lowest in energy. And that was the structure where you had the least separation between the charges on them, so the smallest absolute numbers. If you have formal charges of 0, that's fantastic. That's what the molecule wants. -1, +1 if you must. But when you start having +2, -2, that's a lot of charge separation, so that's less favorable. So we're going to have more examples of that as we go along. But now, what if you had calculated formal charge and they're all the same? How do you know which structure is correct? So what if you have, and this is just some people are having trouble. This is the top of page 4 from the handout. You have 2 valid Lewis structures that have the same formal charge. How do you know where it goes? And the answer is that the negative formal charge should go on the most electronegative atom. And so that's why we're sort of talking about electronegativity again. And so electronegativity, remember, electronegativity is high when the electron affinity is high, meaning that the atom wants to get an electron, has a high affinity for electrons, and also a high ionization energy, which means it doesn't want to give up its electrons. So that's something it likes to have electrons. And so you want to put a negative value, which indicates there's more electrons, on something that's electronegative. So negative on negative over here. And so that's what you're looking for. That's how you're going to make a decision. So let's look at an example. So here is a molecule. And we're going to look at two possible Lewis structures of this with similar formal charges and decide which is the correct structure. So first, let me give you a couple hints that can be useful in problem sets and in exams. When you see CH3, that's a methyl group, and that's going to be terminal. So you're going to have these 3 hydrogens associated with that carbon, and that's going to be at an end of the molecule. So it could look like one of these two things. So we have the carbon, we have it attached to 3 hydrogens, a carbon attached to 3 hydrogens, and then attached to something else, this nitrogen here. And this structure where it's just kind of written out in a line or a chain of atoms, what we call chain molecules sometimes, often the atoms are actually written in the order in which they're attached. So that's definitely true here, CH3, 3 hydrogens attached to the carbon, so they're attached to the atom that came before in the chain. The nitrogen is also going to be attached to the carbon. Even though it follows the hydrogen, you're not going to have hydrogen in the middle of a bond. It's not going to be bonded to 2 things. Hydrogen's always terminal. So even though nitrogen's here, it's got to be attached to the carbon. So we have 3 hydrogens and then a bond between the carbon and the nitrogen. Now we have a hydrogen after the nitrogen, and by this rule it should go on the nitrogen, but you might want to double check that that's true. And then we have an oxygen. Again, the oxygen is going to have a bond with the nitrogen. You're not going to have a bond with hydrogen in the middle. Hydrogen's always terminal. So the only real choice we have here is we can put the hydrogen on nitrogen, or we can put the hydrogen on the oxygen here. And so we can use this rule about electronegativity and formal charges to figure out which of these structures is right. So in this particular case, all of the formal charges are 0 on all of the atoms, except there's one -1 charge. And in this structure, the -1 charge would be on the oxygen. And in this structure, the -1 charge would be on the nitrogen. And if everything else is 0, then you have the sum of your formal charges, -1, equal to the charge on the molecule, which is -1. So both of these are valid structures. Both have low values of formal charge, which is right. So it's going to be the structure that has the negative charge on the most electronegative atom is the right structure. And so here you need to remember, some of your rules about electronegativity. And in terms of electronegativity, we see that oxygen has greater electronegativity than the nitrogen. And so that's where we would want to put our negative charge on. The negative charge goes on the atom that's the most electronegative. And that would generate the lower energy structure. So if you're given a table of electronegativities, which you often are, you can look it up and validate that that's going to be the correct place. And in fact, experimentally, we know that that's the right structure. So that works. So if you have 2 structures, identical formal charges, valid structures, then the last step is to think about where that negative charge should go and pick the atom that is the most electronegative. All right. We have one more thing we need to talk about in Lewis structures before we start violating various rules that we've learned. And that is that we need to talk about resonance structures. And so to explain to you what a resonance structure is, it's really helpful to start with an example. So that's what we're going to do. And we're going to consider ozone, which is 3 atoms of oxygen. And we have the ozone layer, which protects us from UV damage and is very valuable. And we should not destroy it with chemicals being released into the environment. And because you don't have complete say over that, always wear sunscreen. OK. So let's build up these Lewis structures and then consider what's meant by a resonance structure. So here we have part of the periodic table that you're going to need. And we need to think first about the valence electrons. So oxygen has 6 valence electrons, and there are 3 oxygens, so that's 18. To get a full octet for each of the oxygens, 3 oxygens, an octet is 8 valence electrons, so that would be 24. To figure out the number of bonding electrons, we're going to be subtracting our octet electrons from our valence electrons, so 24 minus 18 is 6. And then our next step is to assign those bonding electrons 2 at a time, 2 per bond. So let's take a look at that. We can put 1 bond here between these 2 oxygens, 1 bond here between these 2 oxygens, and then ask, do we have any more? And we do, because we had 6 bonding electrons. We used 4, so we have 2 more bonding electrons. So we need to make a double bond. But now we have the question of where to make that double bond. Am I going to put it between these 2 oxygens, or am I going to put it between those 2 oxygens? And so I could say put it there. But I could also, in structure 2, put the double bond over here. All right, we'll come back to that question in a minute. Let's first figure out if we have any remaining valence electrons, and we do. So we had 18, and we've only used 6, so we have 12 left. So we're going to put those in as lone pairs. And so I can put them in over here. 1 set here, 1, 2, 3, 4, 5, 6. And I can also do that over here. 1, 2, 3, 4, 5, 6. And now we have 2 structures, so we need to think about formal charges to see if that can help differentiate structure 1 from structure 2. OK, and let's look at that. Make sure everyone's ready. And that is a clicker question. So I'll put that back up. All right, let's just take 10 more seconds, and we'll talk about what the right answer is and a little bit of a trick for doing these perhaps a bit faster. OK, so that was pretty good. So let's look at why that's the right answer. And we'll take a look at that over here. So let's do the calculations. So you have to remember the equation for formal charge for sure. And once you do enough problems, it should stick in your head pretty easily. So if we look over here, so this is the formal charge on oxygen A. And there were 6 valence electrons. There are 4 lone pair electrons minus half of the bonding electrons. There are 8 bonding electrons, so that's 2. So that's a formal charge of 0. For oxygen B over here, we again have 6 valence electrons, and we have 2 lone pair electrons. We have 6 bonding electrons, so half of 6 is 3, which is +1. And on oxygen C over here, 6 minus 6 lone pair electrons, half of 1 bond, so half of 2 is 1, minus 1. Overall, the charge here is neutral, and that's good because it's a neutral molecule. So to do this structure faster, you have to realize that oxygen A over here is the same as C over there. So you can just copy down what you had for C is now A. B is exactly the same in the 2 structures, so it's the same as what you calculated. And now this C was the same as this A, so we can put that same value that we calculated for A into C. So they're both the same. same formal charges, which structure is correct? And the answer is both of them, and in fact, you need both of them. So there's data, chemists love data, and the data is that the bonds are actually equivalent in the molecule. So it isn't that there's one double bond and one single bond. There's just one kind of bond in ozone, and it's between a single and a double bond. And so this is how one would draw that kind of thing. You would have structure 1 here and structure 2 here. You would put them both in brackets, and you would put this special double-headed arrow between them, and that indicates that both of these structures are needed to describe the properties of the molecule. You do not have a stationary double bond and a single bond. You have kind of a mixture between these two, and that's what a resonance structure is. So let's take a little bit more of a look at this. So this is just what I had before. The experimental evidence is that the bonds are equivalent. There isn't a double and a single. There's something in between, a 1.5. And this is called a resonance hybrid. And it's a blend of these two structures. So this structure is blended with that structure. So some of you are aware of hybrids from biology and now with cars. So a mule would be an example. And if you're thinking about what a mule is, you don't walk out into your barnyard one day and see a donkey one day, and you go out the next day and you see a horse. A mule is a hybrid between a donkey and a horse. So if you were a chemist, you would do this. You would put the donkey in brackets and the horse in brackets and put your double-headed arrow. And if you see this, you'd say, oh, yes, a mule. So that is what this is. Both structures are needed to describe ozone. One structure isn't enough. You need both of them. They're in resonance with each other. And so what's true about the electrons in ozone is that they're delocalized across all of these bonds. So there isn't like a double and a single. All of those electrons are delocalized. They're shared over this set of atoms. And you can have 2 resonance structures. You can have 3. You can have 4. It depends on the molecule in question. And in all those cases, those electrons would be delocalized. So just to kind of sum that up, resonance structures, 2 or more, same arrangement of atoms, and that's important. It's the electrons that are different. And this isn't in your handout, but just think about this for a second, because it was in your handout a minute ago. Are these resonance structures? No. They are not resonance structures. The atoms are in different positions. So one of these structures is right, one of these structures is wrong. With resonance structures, they're both correct and both needed to define the structure. So pay attention. This is a common mistake. Pay attention. Ask yourself, are the atoms in a different position? That's not resonance. You're just looking, atoms are the same, formal charge are the same. You're just looking at whether you have different arrangements of electrons.